So chapter 2. In chapter 1, you saw how to summarize data. You saw how to look at data from multiple angles, different measures, mean, median, mode, standard deviation, quartiles, interquartile range. You also looked at different ways to plot the data. Histograms, bar charts, stemplots, pie charts, all that. Well, chapter 2 is going to expand on that. In fact, in chapter 2, instead of just looking at one variable, you're going to look at two variables at the same time. That means you're going to use values from one variable to make interpretations or predictions about another variable. For example, based on your Alex score, can I predict what your final grade is? Well, I'm going to use Alex score and I'm looking at final grade. Is there a relationship? Do people who do well in Alex automatically do well in the class? Okay, that's one of the questions that I need to answer at the end of the semester. That is using two variables. So what we're going to now see is just like we did graphical displays of one variable and numerical displays of one variable, we're going to look at graphical displays of understanding the relationship between two variables and numerical measures of signifying the strength of relationship between two variables. Okay, so everything we did in chapter 1, we're going to extrapolate in some sense to chapter 2. So the first thing is called scatter plots. And by the time we are done, we'll talk about outliers and all that. So now, this is really the more common situation rather than chapter 1. Most times we are trying to do what is called prediction. Okay? And what do you mean by prediction? You know, if the federal interest rate goes up, should I buy stocks? Should I buy bonds? How do you do that? Based on prediction. You're trying to use the values of one variable to predict some other behavior. Is there a relationship between those two? Okay? So that's what we're really going to do. So let's take a look at this, something which you might be very familiar with. Is there a relationship between the amount of beers you drink and your blood alcohol level? What do you think? Just looking at those numbers, do you see a relationship between the number of beers and blood alcohol level? You would expect a relationship, right? What kind of relationship would you expect? So if I were to draw this, what should I put on the x-axis? Beers, okay, fine. And this is blood alcohol level. What should happen? Blood alcohol, I don't know why it's BAC. Okay. So what should I expect? Okay, something like this? Does that make sense? Okay. You sure it keeps going up? Shouldn't it be like this? We die here. Right? Is it always true? That means if I take two people and give them the same number of beers, will I get the same amount? Will I get the same amount? No, right? So let's take a look at this graph slightly. So here is the actual data that I collected, and look at that. What you said holds true. That is, as the number of beers goes up, the blood alcohol goes up. But we also see different measurements. For example, here is 3, and you can see that there are 3 people with different amount of blood alcohol. Why do you think that is there? What could explain the difference for the same number of beers, different alcohol levels? Yes?
Maybe their weight or how much they drink.
Okay, so the weight of the person matters. What else can affect it? Gender, very good. What else?
Tolerance.
Sorry?
Tolerance.
How do you define tolerance? But isn't that part of the blood alcohol level? No. I don't know. How would you measure tolerance? It's interesting, but I don't know how to measure it. Let's say the same type of beer. How quickly? Very good. The rate at which it's consumed? Yes?
Same thing.
Same thing, okay. What else? What else can affect?
How long since your last beer?
How long since your last beer? That I guess is similar to how quickly you drink. What else affects absorption of alcohol into your system? Food, very good. Okay, so you're actually telling me something very interesting, because all these things tell you why there is discrepancy between the blood alcohol level for the same number of beers. Very important. Okay, so you can see that that difference is actually different at different levels. Here you have a difference like this, here it's like this, here it's like this. Okay, so but you know that the general relationship in this case between the number of beers and blood alcohol level is something like that, which is what we call as a linear relationship. Okay, so that is what we are trying to get at. What is the relationship between the number of beers and blood alcohol level, and what can explain it? And secondly, can we then predict, based on the number of beers you drink, what your approximate blood alcohol level will be? Okay, that's really the question we're trying to answer. So, you actually identified several of the assumptions that we need to consider in this. Okay, so any kind of relationship we form between two variables can be characterized by three things: the form, whether the relationship is linear, curved, so on; their direction, positive or negative; and finally the strength. What is the strength of the relationship? The strength of the relationship tells you how well we can explain blood alcohol level based on the number of beers. If I can explain the relationship perfectly, that means, guys, thank you. If I can explain it perfectly, that means if I say somebody who drinks 5 beers will always have a blood alcohol level of say 0.2, and that is always true, then that's a perfect relationship. So if you go back to the previous thing, if these points all happen to lie very close to this line, that means it's a strong relationship. But if on the other hand, I get a line like this, and I get points like this, very far away from the point, from the line, that is a weak relationship. Okay? So that means the strength of the relationship is three things: the form, whether it's linear or curvilinear really. Those are the two main things we're going to consider. Whether the direction is positive or negative. That positive or negative can be automatically for a linear, for a slope, we say positive slope or negative slope. Okay? If the slope is negative, then it's negative. And finally, the strength. How close are the points to that line? If the points are very close to the line, it's a strong relationship. So, and finally, deviations from the pattern. We'll talk about outliers in a few seconds. So, would you agree that both these are linear relationships? Okay. So we know the form is linear. Which one has a stronger relationship? The one on the left or the right?
Right.
I hang my head in shame. The one on the left. Even though my line's crooked, which is not unusual, aren't the points closer to the line on the left than on the right? So just because the slope is positive on the right doesn't mean it's a stronger relationship. Okay, therefore this is actually a stronger relationship than this. Okay. What about this? Obviously the keyword it says already gives you the answer, but it's curvilinear, and that's that. So both of these are actually pretty strong relationships, but the one on the left again seems to be a little stronger than the one on the right. Okay. Actually, for those of you who know calculus, how would you define this? You have both positive and negative slopes, right? So there could be a point of discontinuity on that one. Okay. So this says no relationships. If no relationship means, what does it tell you? When I say the two variables are no relationships, can you explain in words what that means? Yes. That is true. Explain in another set of words. Give me two variables that have no relationship. Two variables that don't have any relationships. Yes. Weight and eye color. Yeah, that's probably true. Weight and eye color. So, what does that mean? So the value of one doesn't affect the value of the other, right? So in that particular mean goes back to yours, which is neither positive or negative slope, or in fact no slope. That means changing the value of one variable has no effect on the value of the other variable. That means no relationship. Okay? So we're going to test for that. So even though they have no relationship, if they have no relationship, it really doesn't make sense talking about the strength of the relationship. Right? What is the strength of no relationship? What is 0 of 0? Oh, double 0, I guess, but there's really nothing. Okay? So it doesn't make sense talking about the strength of the relationship there. So we already talked about positive linear and positive and negative linear relationships. And both of these you can say are very, what kind of relationships? Weak or strong? Very strong. Both of them are very strong. So, and we already talked about that. Now let's talk about this. Tell me three things. The form, direction and strength for each one of them. On the left hand side, what is the form of relationship between the left and the right? Or on the left one, let's talk about the left. What is the form of relationship? Linear or curvilinear? Yes.
Linear.
Very good. What is the direction?
Direction is positive.
And the strength? Okay. Or weaker?
Yeah.
Fine. Very good. And on the right? Linear, positive. Very good. Okay. Now let's talk about that. Do you see any problems with the graphs, either of them? Anything that might affect the relationship? Anything that looks different? Yes. They have some outliers. Probably this, even this. Right? They look a little different from the rest of the relationship. On the right hand side, we don't have that problem because it really is a really good, strong relationship between those x and y variables. Okay? Now, every time you see outliers, this is the approach I want you to do. Okay? Some of you did it when you were doing your labs. Okay? This is how you want to tackle. Whenever you see an outlier, ask yourself, what would happen to the relationship if I deleted that outlier? In JUMP, you can just right-click on that value and say exclude and rerun the analysis. You will get the same thing, different results. Okay? Why is that important? That tells you the effect of the outlier on the overall relationship. Always very important. You always want to ask, why is that important? Because that outlier could be a mistake you made in terms of writing down the numbers, or it could truly be an outlier. If it is truly an outlier, then we come up with one conclusion. But if it's a mistake, we at least know what that mistake is doing to the relationship. So in either case, anytime you see patterns which don't follow the normal patterns of that relationship, always ask the question, how would removing this change the relationship? You always have to answer that question. Okay? So in this case, I would go and remove that particular point on the top left and see whether the line would get shifted. My answer to that problem, actually I know, because it won't. Okay? So in this particular case, it's not going to get affected too much. So now, fortunately for us, when we draw this plot of one variable versus other variables, which we now call as a scatter plot, we won't have to worry too much. Why? JUMP will automatically create the right dimensions for the plot for us. But typically what you want to do is fill the whole plot so that you understand the relationship, because you can always skew the relationship by doing something like this. This is the same data, but look at the difference between those two plots. Okay, so you always want to display it so that you understand the relationship over the complete space on which it's drawn. Now there's a slight problem with this. What if you present two plots, okay, which is a comparison, and both of them, when you do this, gives you different scales? How would you handle that problem? If I have two plots, and I'm trying to tell you, oh, look at this plot and look at this plot, but they have different scales, how would you look at it? Or how would you present that problem to me? Suggest some ways of tackling that. You know, for example, this plot starts at 120 and goes up to 160. And let's say I have another plot here. In this case, it goes from 0 to 180. Now what? Obviously, the one on the left-hand side is depicted fully. The one on the right-hand side is not. Can you think of what to do? You could transform the scale so they are similar. That's very good. What else can you do? Yes?
Put them on the same graph.
You could put them on the same graph, trickier, but JMP allows you to do that. So that means I can have one axis here of one scale and another axis here of a different scale, but of the same height. Okay, and I'll show you that how to do that. You can actually do multiple axis, y-axis on the same plot. You can do that. Or thirdly, if you can't do that, if you're limited by your capabilities, you can actually write about it, making sure that people understand there are different axis scales. Okay, but what is the final conclusion on that? The conclusion is that you have to be very careful when you're comparing data, that you're comparing, in this case, bananas to bananas. Okay, same thing. You have to make sure, if it is not clear from the graph, make sure the reader knows that. Then at least when you look at the data, you're looking at the value rather than where they are in the position. Okay, so I'm giving you just a heads up on when you plot your graph, because you are going to do comparison, especially in your project. That will be one of the things that you have to watch out for. Okay. So in this particular case, there is given an outlier there. And what are outliers? Outliers are points that fall away from the normal pattern of data. There are many reasons for having outliers. I told you, incorrectly coding the value, they are actually an outlier. That means the value actually appears, or the value has been captured under circumstances where the rest of the data has not been captured. Okay, for example, you might be measuring soil samples, and they measured 100 samples, and then one of them was captured after a heavy rainstorm. Probably messed up the sedimentation there in that soil, and it comes up as an outlier. The key is, anytime you observe outlier, ask yourself why. Why is it an outlier? What would happen if I deleted the outlier? Okay, those are the questions. So you have to always be curious about patterns that are different. I don't care whether you call it an outlier or not. Just be curious about it. So the more you can dig into that to understand what is going to happen. I was really happy that some of you actually deleted the outlier we had last time, and you noticed that a symmetrical distribution became skewed, which is really good. Okay, that's the kind of things you have to look out when you do these kind of analysis. Okay. So the question is, why is this not an outlier? Well, even though not because they write it. Can you tell me why it's not an outlier? Yes.
So it goes along with the linear positive correlation.
Okay, you use words I have no idea what they are.
Well, it's
Linear
not
positive
straight,
correlation.
It's not actually straight away from the norm of the line.
Oh, or in other words, if you do drink that many beers, your blood alcohol level will be that amount. So it is along the same pattern. As long as it's the same pattern, even though it's different from the rest, it's not an outlier. But this one is, because this is different from the pattern that we have constructed for the rest of the data. Therefore, it is an outlier. Okay, so just because something is far away doesn't automatically make it an outlier. That's why plotting it becomes very interesting, because you can immediately see that. Okay, so. Okay, so this is for you to tell me what's happening. The x-axis is IQ score and the y-axis is GPA. And the question C says, what is the deal with these people? I have no idea what the deal is. What is the deal with these people? So this person has a relatively medium IQ but a very low GPA. A low GPA in this case is 0.5. I don't know how you do that. But and the other person has a low IQ but a high GPA. Can you explain that?
One works hard, one doesn't.
Sorry?
One works really hard, studies. The other one maybe is semi-smart, but just doesn't go to class or anything.
Okay, so the person who got a high GPA studied hard and got a high GPA, even though he had a low GPA, low IQ, and the other one didn't study at all. Possible. What else can you think? What other things can you think about IQ and GPA? What is the basic assumption you're making? IQ measures what? Supposedly. Okay, mine was all zeros, so you know where I stand. So IQ measures intelligence. What does GPA measure? Oh, what is GPA measuring? Your grade. So what is the first assumption you're making there? Okay, I don't know what correlation means, but I'll take the other words. That IQ and grades are related. That means, I shouldn't say this, right? That you don't need an IQ in this class to get a good grade. There's no relation, right? But first you have to show that there is a relationship between intelligence and the grade you get in a class. That's the first assumption you're making. Just because the data shows supposedly what kind of a relationship here? Positive and linear, doesn't mean there is indeed a relationship between IQ and grade. Maybe for this class. The first basic assumption you're making is that IQ and grades are related. What is the second assumption that may be more true than the first one? What's the second one? Yeah, if you have a high IQ, maybe there is a work ethic that goes with it, which automatically leads to the same work ethic explaining GPA. That could be it. We don't know. Okay. So in this case, there are a lot of things we can actually examine and answer because we just sort of assume that, there's a relationship between IQ and GPA. I don't know if that is true. Because intelligence quotient measures something else and GPA measures something else. What may be true is there is something common to both of them. And that's what's capturing the relationship. Okay, that's the important part. So that's what you have to look at in any data set. So we have talked about variables which for most part are quantitative. Both of them are quantitative. IQ is quantitative, GPA is quantitative. Well, what do we do when we have categorical or qualitative data? We can't just plot it. Okay, this was the one about the native species that we had 4 different ones. We can't just plot it. If you plot it, you'll get a positive linear relationship. But do you see a positive relationship? No, each one of them is a negative relationship. Okay, so when you have categorical data, you have to plot it by category. You can't just do this. Okay, so that's the first thing you need to worry about when you're doing categorical data. So here is the relationship between year and the record 10K time in seconds for men and women. Okay, what do you see? Tell me which gender is improving faster. In terms of time. Women. Do you see that? Look at the slope. Okay, women are reducing the time in a much faster rate than men. Okay, both have negative relationship. That means as the years increase, the time falls in seconds. Okay, so you see that relationship between men and women. So when we have categorical data, plot them separately to understand the relationship. Do not put them all in the same graph. It'll mess it up. Okay. So this is lean body mass and metabolic rate. Tell me what you see about the relationship between men and women. Women are the dark, fully covered ones, and the men are the hollow circles. What do you see? In this case, males have typically larger values, but the women have a stronger relationship to metabolic rate. Right here. Okay, so the men is not as strong a relationship, even though they have larger metabolic rates. So larger metabolic rates is a function of what in this case? What can you say about the larger metabolic rates? They are related, but not as strong a relationship. Could metabolic, anybody here in health sciences tell me something about metabolic rates? No, that means I can lie. Yeah, okay. Take a look at this. Tell me what the x-axis is the educational attainment. The y-axis is total income. My first question to you, first of all, what kind of chart is that? Box plots, very good. Second, does the x-axis have to be put in that order? Don't have to be, right? Because each one is a category. But in this case, the order indicates what? From no high school degree to all the way to an advanced degree, correct? Can you read and tell me what is the effect of educational attainment on total income? Let's see how many things you can pull out of the chart.
More education, more income.
More, define more.
The higher the education.
Okay, higher the education, that's fine. When you say more income, more quantitatively, what measure are you using to define more?
$4.
More what? Mean, median, minimum, maximum, range. What are you using? When you say more, what do you mean?
More per year?
Somebody help them out. The statement was the greater the educational attainment, the higher or more the income. The question I asked is what is more? How are you defining more? Not in terms of 5 is bigger than 4, not that way. How do you define the measure for measuring more? Range? Okay, so the range obviously is largest for which one? Advanced degree, right? Okay, range is one. What other measure can you use? The mean. But the problem is, in the box plots, can you tell me what the mean is?
Precisely.
Oh, very close. How would you figure out the mean if I gave you a box plot?
See if it's symmetrical.
Is any of them symmetrical?
And if it is, then it's going to be really close to the median.
Very good. But so in this graph, do you see anything symmetrical?
Not really.
Okay, so we have trouble because we can't find the mean. Can we use the median? And what would the median give you? It will give you the percentile, 50th percentile. Okay. So if you look at the median values, would you agree that the advanced degree has a higher median value compared to everything else? That means as your degree of attainment goes from not high school to advanced, you have a higher median value. Is everybody clear where the median value is? The difference between those two colors? By the way, what are those two colors? They look like teal and some, I don't know what those colors are. It's just confusing. But anyway, the two colors there, right? What else can you say about that? Go back to your range. Make a statement about the range. You can see that if you look at not high school, most people who do not have a high school have a very small range. Correct? What does that tell you? That's right. opportunity for growth in terms of earning capacity is very small. But if you look at the advanced degree, look at the range, anywhere from say 30 to 300 plus. That tells you the opportunity with an advanced degree is much, much higher. So here is a case when the high variability is actually a good thing, looked at it from a totally different angle. I couldn't decide if I wanted to use the word totally or slightly. Okay? So we can talk about smoothing. We're not going to do too much about smoothing because all smoothing does is to try and find out what is the underlying distribution on those curves. Okay, so we'll talk about that when we actually do the problem. So far we have seen a graphical approach to describing the relationship between two variables. Just like we did in chapter 1, let's take a numerical measure to describe the strength between two variables. And that numerical measure is called correlation. Specifically, can you put your phone away, please? Can you put your phone away? Thank you. Specifically, linear correlation. The strength of linear relationship between two variables. And the value varies from -1 to +1. When the value is -1, that means one variable explains the other variable perfectly, but the slope is negative. That means larger values of one variable lead to smaller values of the other variable. When it's +1, the two variables are perfectly related, but with positive slope. When r is equal to 0, that means the two variables have no relationship or zero slope. Okay, so you now know the extent of the values of correlation. And here is a very important point about correlation. It has no units of measurement. Very important. Why is that important? That means I can calculate the correlation of something in the United States and calculate the correlation something in India, say. And I can compare those two values directly because both of them have no units. Okay, so that's a really important part. So, we only measure the direction and strength. Direction is measured by whether it's positive or negative. Strength, the closer it is to 1, the stronger the relationship. Correlation is calculated using both the mean and standard deviation. Because both the mean and standard deviation are affected by outliers, the values of correlation similarly get affected in one way or the other. Okay, so remember that. Anything that affects the mean and standard deviation will eventually affect the correlation. So, in this particular case, because we are calculating mean and standard deviation, and they are only calculated for quantitative variables, correlation is valid only for quantitative variables. Okay, so there are some properties. Here is the formula for calculating the correlation, but let's look at it very simply, okay? All it is we have two variables. Let's call them x and y. For each value in x, subtract its mean and divide it by the standard deviation. That process of subtracting the mean and dividing it by the standard deviation is called standardization. Okay, now let me ask you the following question. Let's say I give you a bunch of numbers. Okay, and let's say those numbers have units in miles. Wouldn't, when I calculate the average of those set of numbers, the average also be in miles? Right? The average is also in the same units as the original numbers. It turns out the standard deviation is also in the same units, miles. So what happens is the numerator is in miles, the denominator is in miles, miles and miles gets cancelled, therefore that value is unitless. No units, okay, unit free. Similarly in y, take the value, subtract the mean, divided by the standard deviation. So all we are doing is standardizing the x values and standardizing the y values so that the units disappear. If there is a relationship between those two, then the standardized values for x and standardized value for y should follow a pattern. If it's a positive relationship, larger values for the standardized x should lead to larger values for standardized y. If the slope is negative, larger values for x should lead to smaller values of y. If you see that pattern, correlation automatically is high. Okay, so correlation, all it is measuring is, in this case, the strength of relationship between x and y. Now, for our case, it doesn't matter which is x and which is y for the moment. All it is doing is saying, here are two variables. Is there a relationship and how do I measure it? So in this case, do you think there is a relationship between pulse rate and time spent swimming? Just by looking at it. There is a relationship. And you expect the relationship to be what? Positive or negative? Negative. So in this case, suppose you were to guess, how strong do you think this relationship is? Is it 0? Okay, is it minus 0.2? Minus 0.8? Minus 0.9? How do you, just give me a guess. 0.8. Okay, negative 0.8. I don't know what the answer is. What is the answer? I didn't calculate it. Sorry. So, negative 0.8 is right, because we don't have an answer. Okay. So, you can see that we are calculating basically the strength of the relationship. The tighter that ellipse is, the stronger will be the value of r. Closer it will be to negative 1. Okay, that's really it. As long as the bounds between those two variables are tighter and tighter, the closer it will be to either negative or positive 1. In this case, negative 1, because I know the relationship is negative. Okay, so we know that. So, and so the key thing is you don't want to do this by hand. And we're not going to do much of it by hand anyway, so. Okay, so we talked about standardization, so we won't get into too much of this. Okay. Negative, who said negative 0.8? Really good. The answer is negative 0.75. So what does that tell you? You guys have a pretty good idea of getting an estimate of how strong the relationship is just by looking at the graph. Okay, that's a good thing to have. If you can gauge the strength just by looking at a graph, that's a pretty good thing to have. Notice in this case, we interchange the x and y axis. The values remain the same, negative 0.75. Because what is it doing? It's only measuring the strength of the relationship between two variables. It doesn't care which one is x and which one is y. We don't worry about it at this point, okay? So, we are going to worry about it in the last half of this chapter. So let's talk a little bit about the properties of correlation. R has no unit. So changing the units of a variable does not change the correlation coefficient because we get rid of all units. So if I take data that's in miles and convert it to kilometers, and the conversion would be 1 mile is how many kilometers?
0.62.
1 mile, okay, 0.62 kilometers. Fine, that's right. 1.6 kilometers a mile, so you're right. So if I convert it to kilometers and calculate this correlation, I'll still get the same answer. Why? Because correlation has no units. In fact, I take any value I get and remove the units from it. So the beauty of it is taking one set of numbers and converting it to another scale does not affect the correlation. That's a very important property. Okay. So in this case, that's what they did. They converted from minutes to hours, and you actually get the same plot that we had before. Okay. So correlation also quantifies the strength and direction, and we have seen this, and here are some examples that you've seen. So this one, correlation is negative, so if I were to draw a slope, it will look like this. This is negative 0.3, you can see that. Okay? So we have seen this, so don't have to worry too much about that. Okay, this is an important property. When the variability of one or both of the variable decreases, the correlation coefficients get stronger. So I'm going to ask you a question. Think carefully about answering this. Suppose, are there two things that I'm interested in? Give me two. I need two variables that you think are related. I do not get that. That's true. I also do not get that. Give me two variables that you might be interested in. How about race is not. Okay, education, no. GPA, income. Okay? Now, let's say I plotted the correlation of this class, taking GPA and income as the two variables. Okay? That's one thing. Secondly, I'm going to take 50 different classes. From each class, I'll take the average GPA and average income. But I have 50 different numbers, okay? Because 50 different class, each class gives me one set of numbers. The average for that class in GPA and the average income for that class. And I plot the correlation. Which one will be stronger? The one which I did with the averages or the one which I did with individual people? To answer the question, think about variability. The averages will be stronger. Which one should have a stronger correlation? Which tends to vary less? Averages or individual values? That means, how different are you from the next student? That is one answer. How different is this class from another class? Which one will have more difference? Individual. Individual differences are greater than group differences for most part. Therefore, the answer to my question is, will the values using averages have a greater or a stronger or a weaker correlation than values using individual values? It will have stronger correlation. Why? Because the variability between averages is smaller. Anytime you reduce the variability, you get stronger correlation, everything else remaining unchanged. Does that make sense? Okay, that's a very important point about correlation. So you can see in this particular case, when the correlation dropped from 0.7 to 0.5, the standard deviation, the correlation went up. Okay, so we have already seen this. It doesn't make sense drawing correlation for this. Okay. Oh, by the way, you know what this is? What do you think that is? What letter is that? Okay, that's the lower case of this. That's my R. Actually, I learned that in drawing class when I had to draw birds. Okay. So this is the other point which is important. Because both the mean and standard deviation are not resistant to outliers, so is the correlation. That means correlation gets affected by those points. So if you delete those points and rerun it, you will get a totally different correlation in many cases. That's why I said, anytime you see an outlier or an influential point, delete it, rerun your analysis to see what it says. That's the way you learn what the data is telling you. Okay, in this particular case, I deleted one point and the correlation jumped from 0.75 to 0.91. Okay, that's really what's happening. So if you want, the book has a free applet which you can go and play around and put dots to see what the correlation is, and you can play around with that I've given you. So let's take a look at some examples. So this is the relationship between manatee deaths and the number of power boats. What is the form of relationship? Very good. What is the direction? Strength. Approximately what correlation? Okay, very good. What about this? Age of women and age of men. Apparently, women always marry men 2 years older than themselves. What would be the correlation? I don't know who dreamt of this example, but okay. Correlation?
1.
Correlation 1, very good. Form is linear, strength is very strong, direction is positive. Okay, so we know that. So why is there no distinction between explanatory and response variables? Explanatory is the variable that will explain something. Like GPA, IQ explains GPA, or height explains weight. It doesn't actually, but so why is there no distinction between X and Y when we do correlation?
Variables?
Because we only care about the relationship between the two variables in terms of the form, direction, and strength, not in the prediction. Okay, so correlation values, we can interchange X and Y, you still get the same values. Okay, so that's why. So, why do both variables have to be quantitative?
There has to be something to count.
Sorry?
There has to be something to count. So some kind of content or quality or quantity.
Give me right there, the answer right there in that Greek formula there. Why do they have to be quantitative? You have to standardize. To standardize, you need the mean and standard deviation, which you can only calculate for quantitative variables. How does changing the units of measurement affect correlation? It does not. Very good. What are the effect of outliers on correlations? Sorry? It should make it right. It affects them because outliers affect both the mean and standard deviation. Therefore, it affects the calculation. In most cases, outliers weaken the value or the strength of the correlation. Okay? So, why doesn't a tight fit to a horizontal line imply a strong correlation?
No relationship.
That's right. A horizontal line means slope is equal to 0. That means no relationship between X and Y. So there's no point even talking about the strength of the correlation. So in this particular chapter, we are now looking at the relationship between two variables. And we started off this chapter by first graphically displaying that relationship. That graphical display was called scatterplot. We then did a numerical measure of the strength of linear relationship between those two variables. That numerical measure was called correlation. Correlation values ranges from -1 to +1. The relationship between two variables can be defined along 3 dimensions: form, direction, and strength. Form means whether it's linear or curvilinear. For most part, we are measuring linear with correlation. Direction, whether it's positive slope or negative slope. Positive slope means both variables either increase together or decrease together. And strength means how good is my line or curve explaining the relationship between the two variables. The closer the points are to the line, the stronger the relationship. We are now going to extend that discussion, but we are now going to differentiate between those two variables. Let me call those two variables X and Y. X is what I'm going to call as my predictor or explanatory variable, and Y is going to be my response or predicted variable. What does that mean? It means I'm going to use the values of X to predict the value of Y. For example, if I want to predict weather, okay, I could use an X variable, which is the pressure. I could say, based on the barometric pressure, this is what I think will happen to the weather. So X becomes the explanation, Y becomes the prediction or response. When we do that, when we differentiate between X and Y, and we use one to predict the value of the other, we are falling into a least square regression mode. We are still going to talk about the strength of linear relationship, but we are now going to differentiate between those two variables. So you might think, is this the same as correlation? The answer is yes and no. It is the same in that we are measuring the strength between two variables. It is not the same in the sense that there is one X and one Y. In correlation, I don't care what is X and what is Y. Okay, that's the big difference between correlation and regression. So we now need to pay attention to which variable is the explanation and which variable is the response. Okay, so we know that correlation measures both the strength, which is the direction, and the direction of the relationship. Okay, so let's take a look in this particular case. So in this case, it says abundance per 10,000 kilograms of prey. You know there is a relationship between a carnivore's body mass and the amount of prey they need. Okay, I mean, you know that there is a relationship. So the question now is, what explains what? Will the amount of prey explain the body mass, or will body mass of a carnivore explain the amount of prey available? What do you think happens? Yes? That is true, but in this case, which one would we call X and which would we call Y?
The carnivore body mass is X.
That's independent?
Yes.
So that means their body, the carnivores, whether they exist or not, doesn't depend upon whether we have prey or not?
No, so.
Oh, well, what if I reverse it? Suppose I say body mass or abundance of prey explains carnivore body mass. Will that make sense?
Yeah.
Sure? Just because we have a lot of prey doesn't mean we suddenly have a big carnivore? Not that easy, right? Some cases it's not that easy. It really depends upon the question you're trying to ask. Okay? So let's take a look at it. So, but in this case, let's assume that X is body mass and Y is prey. And you see there are multiple lines. The question is, which line best explains the relationship between X and Y? That's the question we're trying to ask. Okay? So, okay, we already think this. So here is our example that we know very well. The number of beers and blood alcohol level. Now can you tell me X and Y? Very easily in this. Right? Number of beers is the independent variable, or X, or explanatory variable. So that explains what your blood alcohol level is. Does that make sense? Right? The number of beers explains your blood alcohol level. The question now is, what is that relationship? Or in other words, what I'm asking is, we know there is a relationship, we know it's linear, the direction is positive, and it's relatively strong relationship. But can I categorize that by a line? So what I'm really looking for is a line that explains the relationship. Again, you've got to imagine that's a straight line. Okay? That there is a line that explains the relationship between X and Y. Why do we need a line like that? Well, here's the interesting thing, right? So if somebody comes in and says they drank 7.8 beers, I don't know how that happens. If my line indeed explains the relationship between number of beers and blood alcohol level, then based on this line I can tell that their blood alcohol level is approximately 0.13. Now, none of the people that I actually tallied drank 7.8 beers. But I can use this line as a prediction tool. That means the line can be used to predict values which we have not observed. Okay. Having said that, I'm going to give you a caveat to this problem. The prediction is only valid for values or the range of values for which you have already observed. That means it can only be used between this point and this point. What if I ask you now, somebody who drank 23 beers, what will the value or the blood alcohol level be? The answer is, I cannot use this model to predict that. That is called, when you use a model to predict beyond the range of data that you have observed, it is called extrapolation. Okay, using a model beyond the range of data you observe is called extrapolation, and you really, really have to be careful about that. Okay, so we already saw this problem with the first problem. Do calories explain sodium amounts, or do sodium amounts explain calories? That's not very clear. So anyway, we know that issue lies. So what is a regression line? A regression line is a linear line that explains the relationship between x and y based on some property we construct. The only question we have to ask is, how do we construct this line? How do we know that's the best line we can construct? To define that, we need to define what is best. Okay? So in this case, the regression line, we use the values of x, which is what we call as the independent or explanatory variable, to predict the values of y, which is called as the response or predicted values. Okay, that's really what we are trying to do. But here is the difference between regression and correlation. The distinction between explanation and response is very important. You have to make the distinction. Okay, so now let me ask you. You see a line there. Tell me what I can use to construct a line that explains the relationship between number of beers and blood alcohol level. What kind of criteria would you use? How do you know the line is good? So I'll give you the extreme case. Would you agree with me that if I were to find a line that passes through all the points, you would say it's a good line? No? You wouldn't. You were shaking your head this way. That's yes or no? Okay, tell me why. Well, not on this case, but if I collected data and I found a line that passed through all the points, wouldn't that be a good fit? No? I mean, remember the example we took where women always married men 2 years older than you? And we had a perfect line. Wouldn't that explain the relationship between the ages of males and females at marriage? So, how come it's not a good line? All I'm trying to do is explain one with the value of the other, correct? So, okay, so let me rephrase the problem. In this case, how would you construct a good line? Define good and tell me how you construct it.
I'd make a line between first and last point.
First and last point, okay. So, let me use a different color. Well, this line is pretty good. It's going between the first and last point. It just needs a slight tilt. Okay, so you would say you need a line something like this. Right? Anybody else want to give me a different criteria or agree or disagree with this criteria? So I'm going to give you an example just to see if this works. Here's my line. All my other points are here. Is that a good line? Okay, so give me a better line then. Yes?
Try to get the line as much through, I guess what you would call it, the middle of the points.
Middle of the points.
Like have an even amount of points are on one side and
Okay.
another, I guess.
Let me see if I can quantify your answer. Okay. So, when I started out, a line that passes through all the points, I would consider it as a good line. Why? But it explains all the data that we have. Okay? It explains all the data. You want a prediction line that explains all the data. This one is obviously not. But there is a way for me to quantify how good a line is to the set of points. What is that? The distance between the line and the point. Any line that I draw, even a line that I draw here, there's a distance for each point. Agreed? If the line were to pass through all the points, that distance will be 0. Clear? So can we look at it another way? Find me a line that minimizes the sum of distances of the points from the line. If I add up all those differences, can you find me a line that minimizes that difference? That would be a line with a good fit. Now here is a slight problem. Would you agree that this distance, if I take the distance between the point and the line, this distance is positive? while this distance would be negative. Sorry? No, if I take the difference between the point and the line. So for the one on all the points above the line will give you positive differences because they have higher values. All the points below the line, because the point has lower values, the difference between the point and the line would give you negative values. Now, if you add these up, all the positive and negatives, it turns out to be the answer is always 0. But I don't really care whether it's up or down. What I care is how far you are. So think of it this way. Let's assume the line is really the average. Let's just assume, okay? And each of these points is an individual value. So instead of worrying about the difference between x1 and x bar, point and the line, let me square this. Would you agree that all the positive values will remain positive if I square the numbers? But all the negative numbers become positive? Would you agree? And the larger that value, greater is the distance of the point from the line. Now think about this. I'm going to write this down. So all I'm doing is what have I done? Does that formula look familiar? What is the difference between a point and its mean squared? Sum of it. You know it as louder. Standard deviation. Variance. All it is nothing but calculation of the standard deviation. So the answer to the problem is as follows. Find me a line where the line represents the mean so that the standard deviation is as small as possible. That's it. If you can do that, that line which gives you the smallest possible standard deviation is the line of least squares. Look at the word, least squares. This is your square. Least means as small as possible. That line is called the regression line. Okay, that's what we are trying to get at. So, and I've scribbled all over it. Okay, but that's really what we are doing. So, we can represent the least squares line as b0 plus b1x. Can you tell me what b0 and b1 are in an equation of a line? Since most of you have done your mathematical readiness in Alex. What's b0 and b1? They are called the y-intercept and slope. So b0 is the y-intercept, the line where the line meets the y-axis at x equal to 0. And b1 is the slope, the change in the value of y for a unit change in the value of x. So all we have to do is figure out the values of b0 and b1, and we have our line. With the condition that we minimize the distance between the point and the line. Okay, that's what we are trying to do. When we do that, we'll get the values of b0 and b1. So I'm not going to spend too much time on the formula itself. And the formula is there, we won't get too much because most of the time we are going to actually use jump to calculate a regression line, especially for large data sets. Okay, so some of you who have your TI calculator can actually do it right on the calculator. So these are just outputs that tell you where to look for. So we'll come back to this. Okay. So here is the property of the line. I told you to think of the line as the mean, and it is the mean because it actually passes through the mean of x and the mean of y. Okay. Now, what I want you to do is focus on this line. Let's say this is the equation of the line, not this part. It says the line is equal to 0.0144, and instead of 8, think of it as x plus 0.0008. 0.0008 is the y-intercept and the slope is 0.0144. So what are they telling us? They're telling us I can now use the line to predict based on number of years what the blood alcohol level to be. Okay, so I took an example of 7.8 before. We know that there was no student who actually drank 7.8. So, but I can use my line. So, according to my line, the answer to that is y hat is 0.0008 plus 0.0144 multiplied by 7.8. Whatever answer you get is the predicted blood alcohol level for a student who drank 7.8 beers. Okay, so that's really what you're getting at. So, that's not bad. Okay, let's take a look a little bit at the difference between correlation and regression. In fact, what I told you the difference at the beginning of class, can somebody tell me what it was? What's the essential difference? What is the essential difference between correlation and regression? I've already put one person to sleep. See how many more I can.
It's where the x and the y variables are on the axis.
That's right. So in correlation, it doesn't matter which is x and which is y. In regression, it does. Okay, that's the real essential difference. So let's take a look. You have to be careful on how you choose x and y. In this particular example, if you chose the correct values of x and y, x should be distance and y should be velocity, then you get the correct regression line, which is this. But if you reverse x and y, you get the wrong regression line, which is that. Okay, so you have to be very careful doing a regression on choosing x and y. I keep using x and y. Why? In statistics, it's a convention that x always denotes the set of independent variables and y the response or predicted value. Okay, so even if you look into jump, it will say x and y. So you know that by default you can use that x and y. So let's take a look more specifically at correlation and regression. In correlation, because I do not care about x and y, what we are capturing is the linear relationship in both directions, in both this direction and this direction. But because I care about x and y in regression, what I'm capturing is variation only along this direction. I don't care about this. Okay, so that's the variation that's being captured, only along one axis. That's really the only difference. So the question you might ask is there a relationship between those two? The answer is yes. Correlation is measured by something called R. That's called correlation. And the value of R varies from -1 to +1. The same concept in regression is called R squared. This happens to be the square root of R. Okay, so the question now is, suppose I say R is, let me go the other way. Suppose I say that R squared is 16 or 0.16. Okay, what do you think R is? Oh, you guys, you got to yell at me. Can't you see something wrong I did there? Okay, if R squared is 0.16, what is R? Square root of 0.16 is 0.08. 0.04. You're just giving me answers to a multiple choice question or what? 0.4, right? So I want the square root of 0.16. Are you sure it's 0.4? When you take a square root, what are two possible answers?
Positive, negative.
So how do we know whether it's positive 0.4 or negative 0.4? Can somebody give me an answer?
It would be 0.4 because negative.
What are the three things? Form, direction, and strength. What does direction imply? Slope, right? So here is the answer. If the slope is positive, the answer is positive. If the slope is negative, correlation is negative. Does that make sense? So correlation, the value, if it's negative, tells me I have negative slope. But if you see a positive slope, the answer is going to be positive. Having said that, we know that correlation values are from negative 1 to positive 1. What will the values of r squared be? If r is between negative 1 to positive 1, what will r squared be between? Very good. R squared is therefore between 0 to 1. R squared is called the coefficient of determination. Or think of it another way. It tells you how much of the variation in blood alcohol level can be explained by the number of beers. If R squared is equal to 1, it tells me that blood alcohol level in a person can be perfectly explained by the number of beers. If blood alcohol level is if R squared is equal to 0, it tells me that beers explains nothing about the blood alcohol level. So the value of R squared, the higher it is, closer to 1, the more we can explain about Y using the value of X. Okay, that's what R squared is. So that's the relationship between those two. We already seen this. We don't need to get into this. We will not get into this. Okay, let's talk a little bit about extrapolation. I think this is a very interesting. The x-axis is age in years and the y-axis is height. And it talks about the problem of extrapolation, right? So according to that, if I use the same model, pass the data, by the way, the example there, they said, look at the line passing through all the points. Of course, that's not necessarily true, right? Because not everybody grows at the same rate. So it's completely artificial. So according to this, somebody who's 30 years old should be 105 inches, according to this model. And of course, given how old I am, I'm probably at 1,342 inches. So you really can't see me at this point, but okay, so yeah. So we know this, right? So what about the y-intercept? Well, the same model that we use, the y-intercept here is negative. What does that tell you? We're basically saying that if you don't drink any beers, your blood alcohol level will keep going down. Doesn't make sense. Okay, again, the y-intercept is sort of a logical thing that comes from the thing, but you can only use the model in this case between this value and this value. That's where it's valid. Anything past those two values, the extremes, is called extrapolation, and we don't get into that. Okay, so that's your R squared, and we already talked about that. So I just want you to know the relationship between R squared and correlation. So R squared is the square of the correlation coefficient. Okay. So here are some examples. Why is R negative 1? Very good. In the second example, does X explain anything about Y? Fine. Even though it's perfect, right? So that's a perfect no explanation. And so in this case, you can see that R squared is 0.76 and R is 0.87 positive because the slope is positive. Okay, so two things. the value of r or the sign of r depends on the slope. 2, this is only valid when there is a linear relationship. If your plot looks non-linear, curvilinear, do not use r or r squared for that matter, because it won't be valid. If your plot contains outliers or influential points, again r and r squared are both affected by those. Okay, so every time you plot it, always ask, are there points which look very different from the rest of the data? If the answer to that is yes, delete it and rerun your analysis to see what happens. That will give you more insight into the data than anything else. Okay, so I think some of you actually suggested the answer to this problem long time back, because the amount of beers by itself is not perfectly going to explain the blood alcohol level. Why? Because there were things like how quickly they drank, what they ate before they drank, how heavy they are, so on. What if we include the person's weight? So we do beers per weight to see, and then use that to predict blood alcohol level. See, what do you think will happen to R squared? Will we explain more about the blood alcohol level, or will we explain less? And that's exactly what's going to happen. Look what happened. Blood alcohol R squared now is 0.81. It jumped all the way from 49% to 81%. I can now explain 81% of the variation in blood alcohol level just by using a variable called beers per weight. You have removed the effect of what we call as a lurking variable, a variable that we did not consider before. But now that we have considered it, we get a better estimation of it. Okay, I have no idea what the twin picture is doing there, but so. Okay, what's the answer to this? If class attendance explains 16% of the variation in grade, what is the correlation between percent of classes attended and grade? In fact, 16% means R squared is 0.16. Therefore, R is, we know, 0.4. The only question now is, should it be positive or negative? What do you think? It should be positive. You never know, right? But it should be positive. So, okay, that's weak correlation. So what we have seen so far are ways of studying the relationship between two variables. Okay. But anytime we do that, you really have to be careful what conclusion you're coming to. Just because the number of beers affects blood alcohol level, suddenly we can't go from that to saying beers causes blood alcohol level. Okay, you know that now if you look at cigarette packs, it says that smoking can cause lung cancer. Okay, for that statement to appear as a causation took more than 2 decades. It's a long process that takes before X causes Y. We can make that statement. We can say that X affects Y and put it down. We can say definitely drinking more beers causes higher blood alcohol level. But to make that causation requires a lot more proof. So what this next section is about is really looking at things that might affect our interpretation of the results, and it even might affect how the results turn out. Okay, that's why it says caution about correlation and regression. So let's take a look first at residual plots. We talked about this. Since correlation values are dependent upon calculating the deviation or standardizing the values, if instead of individual values we use averages, correlation and then by definition regression will give you a much stronger relationship than you would expect on an individual platform. Okay? So if you're using averages, automatically assume your values, your R squared correlation values will all be much stronger. So you have to be careful about that. So if we are going to, for your project, you're going to get data on different states. So instead of looking at data individually, if you start summarizing them by county or by state and start looking at averages, your results will be much stronger, which doesn't necessarily make it right. Okay, so be careful about that part of it. So, second one, residual. What is a residual? The residual is the difference between what you observe, which is the point, and what your line predicts the value to be. What you want is a line that passes through all the points, in which case the residual will always be 0. But in this particular case, these have positive residuals, these have negative residuals. All points below the line have negative residuals, all points above the line have positive residuals. What is the residual again? The difference in height between the individual observation, this one, and what the line tells you that value should be. So think of it another way. What we are trying to do is find a line that minimizes the sum of residuals squared. That's what we are trying to do. Find a line that minimizes the sum of residuals squared. Okay, that's really what we are trying to get at. But this leads us to the next problem, which is, even if I were to find a line, is that line appropriate? That's the question that we're going to ask. To do that, is the line appropriate? We look at something called the residual plot. So for the line I showed you in the last page, I drew the residual plot. So x-axis here is the same x-axis that I have here. The y-axis is the residual, which is the difference between the point and the line. So would you agree, take a look at the first point, would you agree that this residual is going to be negative? Because the value is below the line? That value is right here. Similarly, if you take a look at the second point, which is right on it, the residual value should be 0. And that's exactly what you have. What you want, first of all, can you see any pattern in this? Do you see a pattern of the residuals on the graph? Anybody notice any pattern? Is there some sense on the graph, or does it look all random? I don't know what the heck random means, but I'll use it anyway. Maybe I'm cursing you now. Yeah.
It looks like for most of them there's a matching
Up and down.
Up value of positive, value of negative.
So in some sense there's sort of a scatter, evenly scattered around the plot. This is actually a very good residual plot. If you cannot make sense of the plot and it looks all scattered evenly, that tells you that the line we use is a good line. If you see a pattern, that means the line that we constructed is not appropriate for the data. And I'm going to show you some examples of that. Okay, so you really want a residual plot which is randomly scattered about x equal to 0 or y equal to 0. Sorry. Okay. So here is another example. So this is basically what I just talked about. So I'm not going to again. Let's take a look at this. So this is the kind of plot we want to look at. That's the kind of plot we are aiming for. If you see this, can you tell me what happened here? Notice the pattern. First you have negative residuals, then a stream of positive residuals, and then negative residuals. Yes? Oh. So when you see that, it means the line, the linear relationship is not appropriate. There's actually a curvilinear relationship between x and y. Okay? Because it's linear, you see this pattern. What do you see in the last one? The last one you see the following. As you grow from small to large, you see an increasing diversion of points. This is a perfect example. When you plot something that happens over time, let's say you have a machine. Would you agree that over time the machine becomes less and less reliable? Therefore, more and more errors creep up. Therefore, the variability keeps going up. That's a perfect example of that. When you're collecting that, so a lot of times in industries, we plot these over time, and if we see this pattern, we know that the machine is starting to go bad. So many of you have laptops which have been purchased in the last 2-3 years, right? Now, do you know when you start up, there is something called a smart diagnostic of the data? Do you know what that is? So there's a piece of software that's running in the background which is analyzing how reliably you can read and write data. And when that reliability becomes less than certain percentage, your operating system will actually warn you saying your hard drive is about to fail. That's exactly what they're doing. They're checking the reliability periodically, and when that reliability falls below a certain instant, it's telling you that parts of your hard drives are going bad. Okay? So that's a very good, but that's a residual plot that tells me that the model I use has some problems. So again, aim for this. If we get one of these two, we try to modify it so that we eventually land up with the one on top. Okay? So let's take a look at outliers and influential points. I'm going to ask you the following question. Let's see if you can answer this. Here's point, I'll call that A. And here's point which I call as B. Look at the date, look at the line. That's the regression line, okay? If I remove point A, do you think that the line will change much? Why not?
It's an outlier. It's not really good.
It's an outlier, but why doesn't it change the line as much?
I mean, most of the points are very close to the line. If it changes, it's going to decrease.
Right, so that means the influence of that point is very little, right? What if I remove point B? Will that change the line? Yes.
It would change more less points unless they're at that part of
Very good. Can you notice that point B is actually pulling the line towards it? Because it's so far along the x-axis, its influence on the line is much greater. So if I were to remove point B, see what happens. So all data is this solid line. If I remove point B, I get this line. Look at how much the line changed. Now this is nothing. In some cases, removing what we call as an influential point will take the slope from being positive to negative in one shot. So in this previous example, if this child here had been here, the line would have been like this. Okay? And if I then remove this point, you get this line. When you have changes in the slope, because removing one point causes it, that one point is influential. Okay? In this case, A is an outlier, but it's outlier only in one direction. And influential points are outliers in the x direction. So in points that affect the slope of the line tend to lie very far away on the x-axis. Points that affect on the y-axis are outliers, which are different from the rest of the data, but may not affect the slope as much. Okay, so that's the thing that you have to. And for us, do I have to understand this? Yes. But do I have to calculate it? Fortunately, JUMP will allow you to calculate these lines very quickly, just by excluding or including points. So for us to get an answer to this is very simple. The fastest way to understand if a point is influential, delete it, rerun the analysis. See what happens. Okay, if the line changes, it's influential. Doesn't change, not influential. That's it. So always plot your data. We know that. Can I ask you this for this one? Should I be calculating R and R squared? Okay. So here is the correlation. I don't know why I gave you this. But in all these cases, for which one should I be using R and R squared and for which I should not?
And C.
C, should I be using it? What about this guy? So I should delete it and then use it. Same with this person, right? There's one person, but this doesn't make sense. Okay, so the only one which is automatically is there. This one doesn't work because the relationship is curvilinear. Okay, so good. I don't know why. So I'm going to give you 2 examples. We'll see what lurking variables are. There's a strong positive association between number of firefighters at a fire site and the amount of damage a fire does. Is there something missing in that? What would explain that? So what are they saying? The firefighters are not doing the job or what? Yeah.
The greater that, the larger that the fire is, the more firefighters are required to fight it, which is why the fire causes more damage.
So the variable we didn't consider is
How big the fire is.
exactly. See, we left out that variable. That explains both of them. Isn't it? The size of the fire explains both the number of firefighters and the damage. That's your lurking variable. Thing we didn't consider. What about this? Oh, not the wine glass. What about this? No, I wouldn't mind a wine glass with wine. And I always blame my drinking on you guys. You drive me to drink. What's the explanation here?
And well, there's I see too.
Okay.
It'd be like, just because a lot of people when they drink they smoke, so smoking would, like, how many of those drinkers were smokers too? But
Okay.
the other thing would be
But this is negative association. That means if you drink, the death rates actually fall.
oh, I see. Oh, okay. Well, then I know.
You're killing more people
Wait,
than
you're
this.
saying that less people die from heart disease?
No, they're saying there is a negative correlation or association between the amount of wine and death rates.
Wouldn't it be like a bell curve? Because between 2 points, after you drink too many, it's probably bad. If you don't drink enough, it's probably bad. But within the range.
Yeah, but that's still not explaining this, right? You're right. It's a curve, but not explaining it. Yeah.
Could it be as you get older, you're less inclined?
Okay, you guys are okay. Did you look at the whole sentence?
Yeah.
Okay, fine. Then go ahead. Feel free to be right or wrong.
People are older, drinks less alcohol, therefore an older person will get heart disease, a young person have a drink more.
But it doesn't say anything about age there.
True.
Saying wine is good for people who have heart disease.
No. Yeah.
It's in developed nations, so
Aha.
they're going to have better health care, so they'll live longer.
Developed nations. Automatically, you know, developed nations have a higher survival rate. So there are a lot of things that are in developed nations which makes the relationship between moderate amount of wine drinking and death rates totally meaningless. There is your lurking variable, okay? So, I don't know what these twins are keep doing in my... We already talked about this. So let's talk about confounding. Two variables are confounded when their effect on a response variable cannot be distinguished from one another. That means these two variables explain the same thing about your response. That's called confounding. Okay? I think I have an example to show that. We already seen a lurking variable. A lurking variable is a variable that we did not consider but could explain either the response or the explanation or both. Okay? In the previous example, we saw that the size of the fire explained both the number of firefighters and the damage. Okay, so we saw that. So let's see if I got an example for confounding. I'll come to that. Do not use regression on inappropriate data. We know that. Beware extrapolation. Okay. So where's my... Okay, let's take a look at this. First one. Daughter's body mass index depends on mother's body mass index. This is an example of causation. In fact, do you know what percentage of your body mass is inherited from your parents? Anybody? So I can lie again.
20%?
Huh?
20%?
Yeah, actually it's around 20%. That's about right. So it's around 20% that your body mass index is influenced. A lot of it is influenced by culture, social, all those other factors that go into it. Okay. The second one, married men earn more than single men, therefore I should raise my income by getting married. So, you know it's not causation, so we won't get into that. Okay. So here's another example. Shoe size and reading index. Strong association. Would you agree? No, but not causation. Right? That's an obvious example. Okay, let's try this. Students who have high SAT scores in high school have high GPAs in their first year of college. And that is explained by both of them are coming from a common response, which is your innate ability or steady habits. That explains both. So when you have something like a common response explaining two things, that's what we categorize it. Okay? So the second one is, we already talked about lurking. I'm trying to find you an example for confounding. Let me see if I have one for confounding. Here's one. Religious people tend to live longer than non-religious people. In my case, I'm surprised I'm still alive. I'm dead. I'm a Hindu. I'm reincarnated. You like my new form? No? Why? Because religious people also have better habits in most things. They eat better, they're more disciplined, they don't drink wine before coming to class. Everything. So there's something else that is inherent to this whole process, right? So religion by itself is not suddenly making you live longer. But there are variables that affect, which are confounded in this whole process that's helping you live longer. So here are the possible things. So we can have X causes Y, and I'm going to show you, in fact we have talked about that. Smoking causes lung cancer. And how did we come to that conclusion? I'll talk about that in the last slide. There's a common response. That means a single thing, your innate ability or steady habits explains both your SAT scores and GPA. And finally we have confounding, which is religion is confounded with your social habits, your living habits, which basically explains the same thing. Okay, so two things explaining the same thing is called confounding. So we can have these multiple relationships. Let's talk a little bit about causation. And what are you guys smiling away? Can you wait 5 minutes before you send your emergency text for the weekend? So what do we need to establish causation? Several things. A strong association. It has to be consistent, and you have to be able to explain it. That means higher doses of it automatically lead to higher incidence of lung cancer. All these things are now true. In fact, we have come down to the stage that they can say what tobacco does genetically. So causation is very well established for smoking. Okay, but a lot of things, I know there have been always scares. Did you know they did studies on high voltage lines and brain cancer? They couldn't find any causation or relationship. They did, when you buy a cell phone, probably you don't look at it at all, but there is actually a factor that they specify which tells you how much rays or magnetic influence is there in that phone. That means because we use it so close to our head, the presumption is that the higher the magnetic field, greater the impact on your brain. Okay? But they haven't been able to prove that either. So it's a very difficult process to prove causation. Many times we prove causation not by observing, by actually conducting experiments, which is very difficult to do. If I wanted to establish lung cancer and smoking by experiments, this is what I would have to do. I would say half of you have to smoke. Half of you don't smoke. Do that for the next 5 years. I'll talk to you after that. It's not going to work, right? So that's why it takes a long time to establish this causation because of that. So, Okay, I'm going to go drink. Bye.